Imagine your morning. The alarm on your phone wakes you. You scroll through news and messages. You grab your wireless earbuds for a walk. You might use an electric toothbrush. Your smartwatch tracks your steps. Before you even leave the house, you have used many devices, and all of them have one thing in common. They are all powered by batteries. These small, silent power sources are the unseen engines of our modern world. They give life to the technology we depend on every single moment of every single day. We often forget they are there until they run out of power. Batteries are everywhere. They are not just in the small gadgets we carry. They are in our cars, helping the engine start. They are in our laptops, allowing us to work from anywhere. They are in children's toys, bringing them to life with lights and sounds. They are in medical devices like pacemakers, keeping hearts beating steadily. They even power entire homes during blackouts. These little packages of energy have quietly become a fundamental part of our infrastructure. Without them, our connected, mobile, and digital society would simply grind to a halt. The world as we know it would look very different. Think about a world without portable power. Your camera would need to be plugged into a wall. Your remote control would not exist. Your car would need a hand crank to start, just like in the old days. The freedom to move, to communicate on the go, to have information at our fingertips. All of this is made possible by the humble battery. It is a technology so successful and so widespread that it has become invisible. We expect our devices to work anywhere, anytime. This expectation is fulfilled by decades of battery innovation. It is a story of science, engineering, and manufacturing working together. In this essay, we will pull back the curtain on these essential objects. We will journey from their simple beginnings to the complex factories that produce them by the billion. We will explore what a battery actually is and how it works. We will look at the different types, from the tiny cells in a watch to the massive packs in an electric car. Our main destination is the heart of it all, the modern battery factory. We will see how raw materials are transformed into reliable power sources. This is the story of the battery, an object you hold every day but may have never truly seen. So what exactly is a battery? At its core, a battery is a self-contained chemical power pack. It is a device that stores chemical energy and converts it into electrical energy on demand. Think of it like a tiny, controlled power plant. Inside every battery, a chemical reaction is waiting to happen. When you put a battery into a device and turn it on, you complete a circuit. This allows the chemical reaction to start. Electrons begin to flow from one part of the battery to another. This flow of electrons is what we call electricity. It is this electricity that powers your device, making it work. Every battery has three main parts. There is the negative terminal, called the anode. There is the positive terminal, called the cathode. And there is a chemical substance in between, called the electrolyte. The electrolyte separates the anode and the cathode. When the circuit is closed, a chemical process begins. The anode gives up electrons and the cathode accepts them. The electrolyte acts as a gatekeeper, allowing ions to pass through but forcing the electrons to travel through the external circuit, your device. This journey of electrons is the electric current that brings your flashlight or phone to life. This simple principle is the foundation for all batteries. However, not all batteries are created equal. Some are designed for single use. Once their chemical reaction is complete, they cannot be recharged. These are called primary batteries, like the common AA or AAA alkaline batteries. Others are designed to be used again and again. These are called secondary or rechargeable batteries. In these batteries, the chemical reaction can be reversed. By applying an external electrical current, plugging it into a charger, you can restore the battery to its original state, ready to provide power once more. This distinction between single-use and rechargeable batteries is crucial. It shapes how we use our technology and how we think about energy. A disposable battery in a smoke detector is perfect for long-term, low-power use. A rechargeable lithium-ion battery in a smartphone is essential for a device that is used heavily every day. The science inside each type is tailored for its specific job. Understanding this difference is the first step to appreciating the incredible engineering that goes into designing and manufacturing each and every battery we rely on. It is a universe of chemistry in a small, portable package. The story of the battery did not begin with the digital age. It began over 2 centuries ago with a curious observation involving frog legs. In the late 1700s, an Italian scientist named Luigi Galvani noticed that a dead frog's legs would twitch when touched with 2 different types of metal. He believed this was due to animal electricity. However, another Italian scientist, Alessandro Volta, had a different idea. He suspected the electricity was not coming from the frog, but from the metals themselves. This disagreement sparked a scientific revolution and set the stage for a world powered by portable energy. To prove his theory, Volta created what is now known as the voltaic pile in the year 1800. He stacked alternating discs of zinc and copper, separating them with pieces of cardboard soaked in salt water. When he connected a wire to the top and bottom of the stack, it produced a steady, reliable electric current. This was the world's first true battery. It was a monumental invention. For the first time, humanity had a continuous source of electricity, not just a fleeting spark of static. Volta's pile opened the door for countless experiments and discoveries in the newly emerging field of electricity and chemistry. Following Volta's breakthrough, the 19th century became a golden age for battery development. Scientists and inventors across Europe and America tinkered with different chemicals and materials to create better, longer-lasting batteries. In 1836, the Daniell cell improved on Volta's design, making it safer and more practical. Then, in the 1860s, the French inventor Georges Leclanche developed a new battery using a zinc anode and a manganese dioxide cathode. This design, known as the Leclanche cell, was the direct ancestor of the common zinc-carbon batteries that powered the first flashlights and radios for decades. The invention of rechargeable batteries marked another huge leap forward. In 1859, Gaston Plante created the first practical lead-acid battery. This was the first battery that could be discharged and recharged multiple times, making it incredibly useful for storing energy. This is the same basic technology that is still used in the car battery under the hood of most gasoline-powered vehicles today. From a twitching frog leg to a stack of metal discs to the first rechargeable cell, these early discoveries laid the chemical and electrical groundwork for the billions of batteries that are manufactured in factories around the globe today. Our journey into the world of batteries now brings us to the present day. We have seen how a simple chemical principle powers our lives. We have touched on the long history of invention that made it all possible. Now it is time to step inside the place where this magic happens, the modern battery factory. These are not simple workshops. They are highly advanced, incredibly clean, and precisely controlled environments. Here, raw materials like lithium, graphite, manganese, and zinc are transformed into the sleek, powerful batteries we know and use every day. It is a process of immense scale and precision. In the sections that follow, we will take a detailed tour of one of these amazing facilities. We will follow the journey of a battery from start to finish. Our tour will begin with the raw materials. We will see how massive rolls of metal foil are coated with carefully mixed chemical slurries. This step is the heart of the battery, creating the anode and cathode that will store and release energy. The precision required here is astonishing. The thickness of these coatings must be controlled down to the micron, a fraction of the width of a human hair, to ensure the battery performs reliably and safely. Next, we will move to the assembly line. Here, the coated foils are cut, stacked, or wound into tight spirals, depending on the type of battery being made. Whether it is a cylindrical AA cell or a flat rectangular smartphone battery, the process is one of meticulous layering. The anode, cathode, and a special separator film must be perfectly aligned to prevent short circuits. Much of this work is done by automated machines in dry rooms, which have extremely low humidity. This is because the chemicals inside are highly sensitive to moisture, which can ruin a battery before it is even finished. Finally, we will witness the finishing touches. The assembled battery components are placed into their final casing. A small amount of electrolyte is injected, and the cell is sealed. But the process does not end there. Every single battery must undergo a series of rigorous tests. It will be charged and discharged, checked for leaks, and tested for its capacity and voltage. This quality control is essential to ensure that every battery that leaves the factory is safe, reliable, and ready to power our world. This behind-the-scenes look will reveal the hidden complexity behind one of modern life's most essential products. Our story of the battery, well, it often begins in the 18th century, but some discoveries suggest a much older origin. In 1936, workers excavating a village near Baghdad, Iraq, unearthed a curious artifact. It was a small clay jar, about 5 inches tall. Inside was a copper cylinder, and suspended within that cylinder was an iron rod, held in place by an asphalt plug. Archaeologists dated the object to the Parthian period, around 250 BC. Named the Baghdad Battery, this object has puzzled historians and scientists ever since. Its construction bears a striking resemblance to a simple galvanic cell, the basic structure of a battery. Could ancient civilizations have harnessed electricity? The theory is, honestly, quite tantalizing. If the jar were filled with an acidic liquid such as vinegar or grape juice, it could have produced a small but noticeable electric voltage. While there is no direct evidence of wires or devices it might have powered, its design is undeniably provocative. Some scholars speculate it could have been used for electroplating, coating one metal with a thin layer of another, like silver or gold. This would have required a low, steady current, exactly what a simple battery like this could provide. This would explain a level of craftsmanship in ancient artifacts that has long been admired. Other experts remain skeptical, proposing alternative functions for the mysterious jar. Perhaps it was simply a vessel for storing sacred scrolls, with the metals and asphalt serving to protect the delicate papyrus from the elements. The metals might have degraded over time, leaving behind the structure we see today. Without any accompanying written records describing its use, the true purpose of the Baghdad battery remains shrouded in mystery. There is no definitive proof that our ancestors understood the principles of electrochemistry. The object stands as a fascinating anomaly, a what-if in the long history of human invention and discovery. Whether it was a true battery or a simple container, the Baghdad battery forces us to reconsider the timeline of technology. It serves as a powerful reminder that the spark of human ingenuity is not confined to one time or place. The desire to understand and manipulate the world around us is an ancient one. While the verifiable history of the battery begins much later, this small clay pot from ancient Mesopotamia hints that the fundamental components of electrical discovery may have been in our hands for millennia, just waiting for the right mind to connect the pieces and unlock their incredible potential. It is, truly, an electrifying prologue to our story. Before Alessandro Volta could build his famous pile, the world first needed to understand electricity itself. For centuries, the only known form of electricity was static electricity. The ancient Greeks knew that rubbing amber with fur would cause it to attract light objects like feathers. The Greek word for amber is electron, which is actually where our word electricity comes from. For over 2,000 years, this strange, attractive force remained a mere curiosity, a bit of a parlor trick for the wealthy and a subject for philosophical debate. It was a force that could be created in a brief spark, but could not be sustained or harnessed for any practical use. The 17th and 18th centuries, a period known as the Age of Enlightenment, changed everything. This was an era of intense scientific inquiry, where observation and experimentation replaced superstition. Scientists began to systematically investigate the properties of static electricity. Inventors created machines with spinning glass globes and friction pads that could generate large amounts of static charge. One of the most significant inventions was the Leyden jar in 1745. It was the first device capable of storing a significant electrical charge. It was, in essence, the first capacitor, a close cousin to the battery. The Leyden jar allowed for more powerful and dramatic experiments. Benjamin Franklin famously used one in his legendary kite experiment in 1752, proving that lightning was a form of electricity. These experiments captured the public imagination and spurred further research. However, the Leyden jar had a major limitation. It could store a charge, but it released it all at once in a single, powerful spark. It could not provide a continuous flowing current. the world still lacked a source of electricity that was steady and controllable, something that could do more than just create a momentary flash of light or a jolt. This is where the stage was set for the next great leap forward. The scientific community was buzzing with questions about the nature of electricity. They had learned how to generate it, store it, and discharge it in a burst. They had even begun to suspect a link between electricity and chemical processes, thanks to experiments like those of Luigi Galvani and his twitching frog legs. All the necessary ingredients were there: the metals, the chemical knowledge, and the burning curiosity. The world was waiting for someone to put them all together in the right way to create not just a spark, but a continuous, life-altering flow. The critical breakthrough came from a scientific disagreement. As we touched on earlier, Luigi Galvani believed the electricity he observed came from the frog's tissue, a form of animal electricity. But Alessandro Volta, a professor of physics at the University of Pavia, was not convinced. He hypothesized that the current was generated not by the animal, but by the contact between two different metals in a moist environment. To prove his point, he set out to create an artificial source of electricity, one that required no living tissue whatsoever. He wanted to replicate the effect using only inorganic materials, to show the world the true source of this power. After extensive experimentation, Volta announced his success in a letter to the Royal Society of London in 1800. His invention was elegantly simple. He created a stack, or pile, of alternating discs of two different metals, typically zinc and copper. Between each pair of metal discs, he placed a piece of cardboard or cloth soaked in brine, which is salt water or a weak acid. This soaked material acted as the electrolyte. When he connected a wire to the top and bottom of this tall stack, it produced a stable and continuous electric current, far more useful than the fleeting spark of a Leyden jar. The voltaic pile was born. This invention was nothing short of revolutionary. For the very first time in history, humanity had a reliable and lasting source of electricity. Volta's pile was not just a scientific curiosity, it was a practical tool. Scientists could now perform experiments that were previously impossible. They could study the effects of a continuous current on chemical compounds, a field that became known as electrochemistry. Sir Humphrey Davy, for example, used a massive voltaic pile to isolate new chemical elements like sodium and potassium for the first time, proving they existed within common compounds. The battery had become an engine of discovery. Volta's achievement fundamentally changed our relationship with energy. It demystified electricity, moving it from the realm of natural phenomena like lightning into the world of controlled, man-made technology. The pile proved that electricity could be generated through a chemical reaction, stored, and then released in a controlled flow. This was the foundational principle upon which all modern batteries are built. Every time you charge your phone or start your car, you are using a direct descendant of Volta's humble stack of metal discs and salty cardboard. His invention did not just create a current, it opened the floodgates for the electric age. With the blueprint provided by Volta, the 19th century witnessed a flurry of innovation in battery technology. Scientists and inventors immediately began to work on improving the voltaic pile, which, for all its brilliance, had its flaws. The original pile could not provide a strong current for very long, and it had a tendency to leak its corrosive electrolyte. The race was on to build a better battery, one that was more powerful, longer lasting, and more practical for a wider range of applications. This period became a kind of chemical arms race, with each new design attempting to outperform the last. A significant improvement arrived in 1836 with the Daniell cell, invented by British chemist John Frederick Daniell. His design cleverly solved the pile's biggest problem, a phenomenon called polarization, where hydrogen bubbles would form on the copper electrode, reducing the battery's effectiveness. Daniell's cell used two different electrolyte solutions separated by a porous clay pot. This prevented the bubble formation and resulted in a much more stable and reliable current. The Daniell cell became the first truly practical source of electricity for new technologies like the telegraph, which required a steady voltage over long periods. The next major leap forward was the development of the wet cell by French inventor Georges Leclanche in the 1860s. His design used a zinc anode and a manganese dioxide cathode mixed with carbon powder, immersed in a jar of ammonium chloride solution. The Leclanche cell was more robust, cheaper to produce, and required less maintenance than the Daniell cell. More importantly, it laid the groundwork for the first dry cell. By adapting Leclanche's chemistry into a sealed, paste-based electrolyte, inventors created the first portable batteries, paving the way for consumer devices like the flashlight. Perhaps the most impactful invention of this era was the first rechargeable battery. In 1859, French physicist Gaston Plante developed the lead-acid battery. He placed 2 sheets of lead, separated by a rubber strip, into a solution of sulfuric acid. By passing a current through the cell, he could charge it, and then the cell could discharge to provide power. The process was reversible. This was a monumental breakthrough. For the first time, electrical energy could be stored for later use. Plante's basic design is so effective that it remains the core technology for the starter batteries found in virtually all gasoline-powered cars today. By the end of the 19th century, the fundamental science of the battery was firmly established. The pioneering work of Volta, Daniell, Leclanche, and Plante had created a diverse toolkit of electrochemical solutions. These were no longer just laboratory curiosities. They were becoming essential components of an increasingly industrial and interconnected world. Telegraph networks that spanned continents relied on steady currents from Daniell cells. Early telephone systems used Leclanche cells to power their signals. The groundwork had been laid for a world where power was no longer tethered to a large, stationary generator. The development of the dry cell was a critical turning point in making this power personal and portable. By replacing the liquid electrolyte with a moist paste, batteries could be sealed, made in various sizes, and used in any orientation without spilling. This innovation, commercialized in the 1880s, unlocked a world of possibilities. It led directly to the first consumer battery-powered device, the flashlight, introduced in 1899. Suddenly, people could carry a source of light in their pockets. This simple convenience was a profound shift, demonstrating the liberating potential of portable power for the average person. This era of discovery defined the core chemistries that would dominate the battery market for the next century. Zinc-carbon batteries, direct descendants of the Leclanche cell, would power radios, toys, and gadgets for decades. Lead-acid batteries, born from Plante's invention, became the standard for transportation and industrial energy storage, a role they still hold. The principles of using a chemical reaction to create a flow of electrons, and in some cases, reversing that reaction, were now well understood. The focus of innovation began to shift from pure discovery to manufacturing, refinement, and cost reduction. The spark of discovery, which began with a twitching frog leg and was fanned into a flame by Volta's pile, had now become a steady, reliable burn. The scientific foundation was complete. Humanity had learned how to bottle lightning. The next chapter in the story of the battery would not be about inventing the first cell, but about learning how to produce billions of them. The challenge moved from the scientist's laboratory to the engineer's factory, setting the stage for the mass production that would truly power the modern world and all the devices we now take for granted. When you think of a battery, the first image that probably comes to mind is the small, familiar cylinder of a AA or AAA cell. These are the undisputed workhorses of the battery world, powering countless devices in our homes. From the television remote control to your wireless mouse, from children's toys to wall clocks, these batteries are everywhere. They are a perfect example of a primary battery, meaning they are designed for single use. Once the chemical energy inside them is depleted, they are meant to be disposed of, hopefully through recycling. Their widespread use comes down to their reliability, low cost, and standard sizing. These common batteries are most often alkaline batteries. This name refers to the chemistry inside them. They use zinc for the negative electrode, or anode, and manganese dioxide for the positive electrode, or cathode. The key ingredient that gives them their name is the electrolyte, which is a potassium hydroxide solution, a strong alkaline substance. This chemical combination is more potent and energy-dense than the older zinc-carbon batteries they replaced. This means an alkaline battery can last much longer and provide a stronger, more consistent power output, making it ideal for devices that need a bit more energy, like a digital camera's flash or a motorized toy. The genius of these batteries lies not just in their chemistry, but in their standardized design. The AA, AAA, C, and D cell sizes were established decades ago to create a universal system for portable devices. This means you can buy batteries from any brand, anywhere in the world, and be confident they will fit your device. This universal standard was a crucial step in making battery-powered technology accessible to everyone. It created a simple, interchangeable system that manufacturers and consumers could rely on. The design itself is a marvel of compact engineering, with the anode, cathode, and electrolyte all packed safely into a sealed steel can. While they are incredibly convenient, their single-use nature presents a significant environmental challenge. Billions of these batteries are produced and discarded every year. The materials inside them, while common, can be harmful if they leak into the soil and water from landfills. This is why proper disposal and recycling programs are so important. These everyday powerhouses are a perfect illustration of the trade-offs in battery technology. They offer incredible convenience and accessibility, but they also force us to consider the environmental cost of our demand for disposable, portable power. They are simple, yet their impact is complex. While alkaline batteries are perfect for low-drain devices, the need for a reusable power source for more demanding gadgets led to the rise of rechargeable consumer batteries. Before the dominance of lithium-ion, two main types led this charge: nickel-cadmium, or NiCd, and nickel-metal hydride, or NiMH. These batteries, often made in the same familiar AA and AAA sizes, offered a revolutionary proposition. Instead of throwing a battery away when it died, you could simply place it in a charger and use it again, hundreds of times. This was honestly a game changer for devices like portable music players, early digital cameras, and handheld video game consoles. Nickel-cadmium batteries were among the first widely available rechargeable options. They were rugged and could deliver a high current, making them excellent for power tools and other high-demand applications. However, they had a few significant drawbacks. The cadmium used in them is a highly toxic heavy metal, making their disposal an environmental concern. More famously, NiCd batteries suffered from what's called a memory effect. If you repeatedly recharged them before they were fully drained, they would remember this shorter cycle, and their total capacity would appear to decrease over time, which was a frustrating quirk for users. To address these problems, the nickel metal hydride, or NiMH, battery was developed. It offered a significant improvement over its predecessor. NiMH batteries have a higher energy density, meaning they can store more power in the same size cell, allowing your devices to run longer on a single charge. They also do not suffer from the severe memory effect of NiCd batteries, making them much more user-friendly. Most importantly, they are made with more environmentally friendly materials, replacing the toxic cadmium with a hydrogen-absorbing alloy. This made NiMH the preferred rechargeable choice for consumer electronics throughout the 1990s and 2000s. The rise of NiCd and NiMH batteries marked a fundamental shift in how we thought about portable power. It introduced the concept of an energy cycle use, recharge, repeat. This not only saved consumers money in the long run, but also represented a step toward greater sustainability by reducing the number of single-use batteries being thrown away. While they have now been largely surpassed by newer technologies for high-performance devices, NiMH batteries are still widely used today in many household applications. They represent a crucial bridge between the disposable battery era and the fully rechargeable world we now live in. Today, one type of battery reigns supreme over the world of high-performance portable electronics, the lithium-ion battery. If you think about it, your smartphone, your laptop, your wireless headphones, or your tablet, they are all powered by this incredible technology. Lithium-ion or Li-ion batteries have completely transformed our digital lives by offering an unmatched combination of high energy density, lightweight, and excellent rechargeability. They can pack a huge amount of power into a very small and light package, which is exactly what modern, slim, and powerful personal devices require. This is the technology that untethered us from the wall socket. The secret to the lithium-ion battery's success lies in its core component, lithium. Lithium is the lightest of all metals and has fantastic electrochemical properties, meaning it can store and release a large amount of energy. Inside a Li-ion battery, lithium ions shuttle back and forth between the anode, which is typically made of graphite, and the cathode, which is made of a lithium metal oxide during charging and discharging. This process is incredibly efficient and can be repeated hundreds or even thousands of times with very little degradation. Unlike NiCd batteries, Li-ion batteries have no memory effect, so you can top them up whenever you like without harming their long-term capacity. This technology is not just limited to small gadgets. Lithium-ion batteries are the driving force behind the electric vehicle revolution. By connecting thousands of individual Li-ion cells together into massive battery packs, engineers can create a power source strong enough to propel a car for hundreds of miles on a single charge. This application has pushed Li-ion technology to its limits, driving innovations in energy density, charging speed, and safety. The same basic chemistry that lets you watch videos on your phone for hours is also helping to reshape the future of transportation and reduce our reliance on fossil fuels. Despite their incredible advantages, lithium-ion batteries come with their own set of challenges. The materials inside, particularly lithium and cobalt, are expensive, and their mining can have significant environmental and social impacts. They also contain a flammable electrolyte, and if the battery is damaged, punctured, or improperly charged, it can lead to a dangerous situation known as thermal runaway, where the battery overheats and can catch fire. As a result, every Li-ion battery contains sophisticated safety circuits to manage its temperature and voltage, ensuring it operates safely within its limits. They are the undisputed kings of portable power, but they are also a technology that demands our respect and care. While sleek lithium-ion batteries power our modern gadgets, a much older and heavier technology is responsible for starting most of the cars on the road today. This is the lead-acid battery, an invention that dates all the way back to 1859. For over 160 years, this design has remained the standard for what is known as an SLI battery, starting, lighting, and ignition. Its primary job is not to power the car for long distances, but to provide the massive jolt of electricity needed to turn over the heavy internal combustion engine. It is honestly the unsung hero that brings your car to life with the turn of a key or the push of a button. A lead-acid battery is a perfect example of function over form. It is heavy, bulky, and filled with a corrosive liquid electrolyte, sulfuric acid. Inside its black plastic box are a series of lead plates, or grids, that serve as the electrodes. One set of plates is made of pure lead, while the other is coated in lead dioxide. When you start your car, these plates undergo a powerful chemical reaction with the acid, releasing a huge surge of electrical current for a few seconds. Once the car's engine is running, the alternator takes over, powering the car's electronics and, crucially, recharging the battery for its next job. One of the main reasons for the lead-acid battery's longevity is its low cost and incredible reliability. The materials, lead and sulfuric acid, are inexpensive and widely available. The manufacturing process is mature and well understood, making them cheap to produce. They are also extremely dependable in a wide range of temperatures, from freezing cold winters to scorching hot summers. This robustness is essential for a component that sits under the hood of a car, exposed to vibration, heat, and the elements. Its ability to provide a high cranking power reliably makes it perfectly suited for its specific, demanding task. Another surprising advantage of the lead-acid battery is its status as one of the most recycled consumer products in the world. Due to the value of the lead and the hazardous nature of the acid, a highly effective and widespread recycling infrastructure has been built up over decades. When your old car battery is replaced, it is almost certain to be sent to a special facility where over 99% of its materials can be recovered and reused to make new batteries. In this regard, the old heavy lead-acid battery is a model of a circular economy, proving that even century-old technology can teach us valuable lessons about sustainability. Beyond the common cylinders and rectangles that power our lives, there exists a vast world of specialty batteries designed for very specific jobs. These batteries come in all shapes and sizes, each with a unique chemistry tailored to its application. One of the most common types is the button cell, also known as a coin cell. These tiny, flat, disc-shaped batteries are essential for devices where space is extremely limited. You will find them in wristwatches, hearing aids, small electronic calculators, and on the motherboards of computers, where they provide power to maintain the system clock and settings. Button cells are a marvel of miniaturization. Despite their small size, they are engineered to provide a very stable voltage over a long period, often for years. Different chemistries are used depending on the need. For example, silver oxide cells are often used in watches because they provide a very steady voltage, which is crucial for accurate timekeeping. Lithium coin cells, like the common CR2032, offer a higher voltage and a very long shelf life, making them perfect for applications like car key fobs or the aforementioned computer motherboards, where they might sit unused for long periods but must work when needed. Another category of specialty batteries includes those designed for extreme conditions or life-critical applications. Medical devices such as pacemakers require batteries that are incredibly reliable, have a very long lifespan, and are hermetically sealed to be safe inside the human body. These often use a specialized chemistry like lithium iodide, which can last for a decade or more. Similarly, batteries used in military, aerospace, or deep-sea exploration applications must be able to withstand extreme temperatures, pressures, and vibrations that would cause a standard consumer battery to fail catastrophically. These are custom-engineered power sources built for ultimate reliability. This diversity shows that there is no single best type of battery. The ideal choice always depends on the job it needs to do. A tiny, low-power button cell for a watch has completely different requirements from a high-power, rechargeable lithium-ion pack for an electric drill, or a heavy, high-current lead-acid battery for a car. Each type represents a unique solution to a specific engineering problem, a careful balancing act of cost, size, power, lifespan, and safety. This vast ecosystem of battery types ensures that for every technological need, there is a specialized power source waiting to bring it to life. Our journey into the heart of battery manufacturing begins long before the first machine whirs to life on the factory floor. It starts in the minds of engineers and chemists, in a stage of meticulous design and material selection. Every battery, whether a tiny button cell or a massive electric vehicle module, is a precisely engineered system. The final application dictates every choice. Will it need to deliver a huge burst of power for a moment, like a car battery, or provide a steady, low current for years, like a pacemaker battery? The answers to these questions determine the blueprint for its construction and the specific raw materials that will be used in its creation. The selection of raw materials is a critical first step, a global scavenger hunt for the planet's most electrochemically active elements. For a modern lithium-ion battery, the shopping list is extensive and specific. Giant rolls of paper-thin copper and aluminum foil are procured to serve as the current collectors. Highly purified graphite powder is sourced for the anode, the negative electrode. For the cathode, the positive electrode, a complex cocktail of lithium, nickel, manganese, and cobalt oxides is required. These active materials are the very soul of the battery, the substances that will store and release the electrical energy we depend on for our daily lives. Beyond the active materials, other crucial components must be sourced. A special polymer film, microscopically porous, is needed for the separator. the vital barrier that keeps the anodian cathode from touching and causing a short circuit. A complex blend of organic solvents and lithium salts must be mixed to create the electrolyte, the liquid medium that allows ions to flow between the electrodes. Even the humble battery can, typically made of steel or aluminum, is carefully designed to be strong, lightweight, and corrosion-resistant. Each material is chosen for its specific properties, contributing to the battery's overall performance, safety, and longevity. Once the design is finalized and the materials are gathered, they arrive at the factory ready for transformation. These materials don't just show up in bags and boxes, they arrive in immense quantities, often in a highly refined state. The factory itself is a symphony of logistics, ensuring a constant and pure supply of these essential ingredients. The quality of these incoming raw materials is tested rigorously before they ever enter the production line. Any impurity, even at a microscopic level, could compromise the performance and safety of the final product. This initial stage of design and procurement lays the absolute foundation for the millions of reliable batteries that will soon roll off the assembly line. The first major process inside the factory is the creation of the electrodes, the positive and negative poles of the battery. This is where the raw chemical powders are transformed into the active components of the cell. The process begins in a massive industrial mixing room, which, honestly, resembles a high-tech bakery. Here, the active material powders, graphite for the anode, and the lithium metal oxide blend for the cathode, are poured into giant mixers. They are combined with a conductive additive, typically a form of carbon black to help electricity flow, and a binder, which is a special polymer glue that will hold everything together on the metal foil. These dry ingredients are then mixed with a solvent to create a thick, dark, and perfectly uniform slurry. The consistency of this slurry is absolutely critical. It must be completely smooth with no clumps or air bubbles. Achieving this perfection requires hours of mixing under tightly controlled conditions of temperature and pressure. The anode slurry, which is typically black due to the graphite, and the cathode slurry, often a dark grey or black, are prepared in separate, dedicated mixing systems to prevent any cross-contamination. This meticulous mixing process ensures that every part of the final electrode will have the same chemical properties and perform identically. Next, this precious slurry is transferred to the coating machine, a marvel of precision engineering that can be as long as a football field. Here, the thin copper foil for the anode or aluminum foil for the cathode is unrolled and fed through the machine at high speed. A razor-sharp doctor blade or a series of rollers applies an incredibly precise layer of the slurry onto the foil. The thickness of this coating must be controlled with astonishing accuracy, often down to a single micron, which is 1/1000th of a millimeter. Even the slightest variation in thickness can affect the battery's capacity and lifespan, so laser measurement systems constantly monitor the process. After being coated, the wet foil passes through a long drying oven that can be over 100 feet long. This oven evaporates the solvent, leaving behind a dry, stable layer of the active material firmly bound to the metal foil. The foil is then sent through a set of massive high-pressure rollers in a process called calendaring. This is like running dough through a pasta maker, compressing the coated material to achieve the perfect density and thickness. The result is a massive roll of finished electrode material, the very heart of the battery, now ready to be cut and assembled into individual cells. This is where raw chemistry becomes functional technology. Section 3. The winding road. Assembling the jelly roll. With the massive rolls of anode and cathode material prepared, the next stage is to assemble them into a structure that can be placed inside a battery can. For cylindrical cells like the common AA or the 18650 and 2170 cells used in everything from vape pens to electric cars, this is accomplished through a remarkable process of high-speed winding. The long sheets of coated foil are first slit into ribbons of the correct width for the specific battery size being produced. These ribbons of anode and cathode material are then fed into an automated winding machine, a blur of mechanical precision that carries out its task with incredible speed and accuracy. The machine takes one ribbon of the anode, one ribbon of the cathode, and two ribbons of the porous separator film. The separator is the crucial safety component, a thin plastic membrane that physically separates the positive and negative electrodes while still allowing lithium ions to pass through its microscopic pores. The machine carefully layers them in a specific order: anode, separator, cathode, and another layer of separator. This sandwich of materials is then wound tightly around a central spindle or mandrel, creating a compact, round log. This tightly wound structure is known as a jelly roll or a cell winding, a fitting name for its layered, spiral appearance. The precision required during this winding process cannot be overstated. The alignment of the layers must be perfect. The anode material is always made slightly wider than the cathode to prevent any chance of the cathode touching the edge of the anode, which could lead to a dangerous internal short circuit. The tension of the winding must be exact. Too loose and the battery's performance will suffer. Too tight and the layers could be damaged. High-speed cameras and sensors monitor every single rotation, ensuring that each jelly roll is a perfect replica of the one before it, guaranteeing consistency across millions of cells. Once the winding is complete, the machine automatically cuts the ribbons and tapes the end of the jelly roll to secure it. The finished jelly roll is then ejected onto a conveyor belt, ready for the next step. For other types of batteries, like the flat pouch cells used in smartphones, the process is slightly different. Instead of being wound, the electrode sheets are cut into rectangular pieces and then stacked on top of each other with separators in between. Regardless of the method, whether winding or stacking, the goal is the same: to pack as much active electrode material as possible into a small, defined space, creating a dense, energy-rich core for the battery. Section 4. The dry room, a controlled environment. Much of the battery assembly process, especially for high-energy lithium-ion cells, takes place in a highly specialized environment known as a dry room. This is not just a clean room. It is an area where the level of moisture in the air is controlled to an almost impossibly low level. The air inside a dry room can be over 100 times drier than the air in the Sahara Desert. Workers entering these areas must pass through a series of airlocks and wear special lint-free suits, gloves, and masks to prevent any contamination from their bodies or clothing. The atmosphere is carefully managed and constantly monitored. The reason for this extreme measure is the volatile chemistry inside a lithium-ion battery. The electrolyte and the electrode materials are extremely hygroscopic, meaning they readily absorb water molecules from the air. If moisture contaminates the inside of a battery cell during assembly, it can trigger a series of unwanted chemical reactions. This moisture can react with the electrolyte salt to form hydrofluoric acid, a highly corrosive substance that will attack and degrade the internal components of the battery. This degradation severely reduces the battery's lifespan and capacity, and in a worst-case scenario, it can lead to safety issues. Building and maintaining these dry rooms is a significant engineering challenge and a major cost for any battery factory. Massive dehumidifying systems work around the clock, using powerful desiccants to strip every last bit of water vapor from the air before it is pumped into the room. The rooms themselves are built to be almost perfectly airtight, with sealed walls, floors, and ceilings to prevent any moisture from leaking in from the outside. The pressure inside the room is kept slightly higher than the surrounding areas, so if a small leak were to occur, dry air would flow out rather than moist air flowing in. Working in this environment is demanding for the technicians and engineers inside. The extremely dry air can be uncomfortable, and the need for full-body protective suits adds another layer of difficulty to their precise tasks. All the automated machinery used within the dry room must also be specially designed to operate in these low humidity conditions without generating static or shedding particles. This commitment to an utterly dry environment is a non-negotiable part of modern battery manufacturing. It is a critical, hidden step that ensures every cell is built to last and to operate safely throughout its intended life. Section 5. Bringing it to life. Electrolyte, filling and sealing. After the jelly roll has been meticulously assembled and inspected within the dry room, it is inserted into its protective metal casing, which is usually a steel or aluminum can. For a cylindrical cell, the jelly roll is slid into the can, and an electrical tab from the anode is welded to the bottom of the can, while the cathode tab is connected to the top cap assembly. At this point, the battery is still just a dry, inert object. It has all the necessary components, but it lacks the one final ingredient that will allow it to come to life: the electrolyte. This is the moment the cell gets its soul. The next step is the electrolyte filling process, a procedure that requires extreme precision and care. The open-topped cans, each containing a jelly roll, move along a conveyor to an automated filling station. Here, a precise nozzle injects an exact amount of the liquid electrolyte into each can. The volume must be perfect. Too little electrolyte and parts of the electrodes won't be able to participate in the chemical reaction, reducing the battery's capacity. Too much, and it could cause pressure issues when the battery heats up during operation. The electrolyte itself is a carefully guarded trade secret, a cocktail of organic solvents and lithium salts designed for optimal performance and safety. Once filled, the cells are often left to rest for a period in a process called soaking or wetting. This allows the liquid electrolyte to fully seep into all the microscopic pores of the electrodes and the separator. It is crucial that the electrolyte makes complete contact with every surface of the active materials inside the jelly roll. This ensures that the entire volume of the electrode can be utilized, maximizing the battery's energy storage potential. This quiet waiting period is a vital, unseen step that ensures the cell will be able to deliver its full power when it is eventually called upon to do so. Finally, the battery is ready to be sealed from the outside world. The top cap assembly, which includes safety features like a pressure vent, is placed on the can. A high-precision crimping or laser welding machine then creates a permanent, airtight seal. This seal is absolutely critical to the battery's safety and longevity. It locks the volatile electrolyte inside and keeps contaminants like oxygen and moisture out for the entire life of the battery. The cell is now a self-contained electrochemical power plant, fully assembled and sealed, but it is not yet ready for use. It still needs to be woken up. So the newly sealed battery cell isn't actually a functional power source just yet. It's still in this inert, uncharged state. The next step in its journey is one of the most critical and, honestly, time-consuming in the whole manufacturing process formation. This is basically the battery's very first charge and discharge cycle, a carefully controlled electrical awakening. At this stage, the cells are moved from the main assembly line into these massive racks inside a temperature-controlled room. Here, every single cell is connected to a sophisticated charging system that will, bit by bit, gently apply an electrical current for the very first time in its life. But, this initial charge isn't just about putting energy into the battery. It's actually about creating a crucial internal component. As lithium ions travel from the cathode to the graphite anode for the first time, they interact with the electrolyte right at the surface of the anode. This reaction forms a microscopic stable film called the solid electrolyte interface, or SEI layer. Think of the SEI layer as a perfectly formed skin, protecting the anode from further reactions with the electrolyte. A well-formed SEI layer is absolutely essential for a long and stable battery life, because it lets lithium ions pass through, but it keeps the electrolyte from being consumed in unwanted side reactions. The formation process is really this delicate dance of chemistry and electricity, and it can actually take several days to finish. The charging voltage and current are ramped up very slowly, following a specific profile. During this time, small amounts of gas can be generated inside the cell as a byproduct of the SEI formation. For pouch cells, you might even notice a slight swelling. After this initial charge, the cells are moved to a degassing machine. This machine punctures a small, designated tab on the pouch, releases the trapped gas in a vacuum, and then reseals the cell permanently. It's a vital step for both safety and for the final shape of the battery. But even after the initial formation cycle and degassing, these batteries are not immediately ready to ship. Next, they enter another quiet but essential phase: aging. the fully charged cells are stored on racks in a temperature-controlled room for a period that can range from a week to nearly a month. During this time, their open circuit voltage is meticulously monitored by a computer system. This aging process allows the internal chemistry of the cell to stabilize. More importantly, it serves as a powerful quality control check. Any cell with a manufacturing defect, like a microscopic internal short, will show a slight drop in voltage during this period and can be identified and removed from the batch. After making it through the long aging process, the batteries are finally ready for their last set of exams. This is the final stage of quality control, a rapid-fire series of automated tests to make sure that every single cell meets the exact specifications required by the customer. The cells are sent through a gauntlet of testing machines that check a wide range of parameters. They're tested for precise voltage, internal resistance, and even their exact physical dimensions. High-speed, high-resolution cameras scan each cell for any external cosmetic defects, like scratches, dents, or faulty welds. And honestly, any cell that fails even one test is immediately rejected. One of the most important tests is the capacity check. A sample of batteries from each batch, and sometimes every single battery, is put through a full charge and discharge cycle on a testing cycler. This machine precisely measures how much energy the battery can store and deliver, confirming that it meets its rated capacity in milliamp hours or amp hours. Other tests might include checking the performance of safety features, like the pressure vent, to make sure they'll work correctly under fault conditions. This rigorous, multi-step testing process is really the factory's final promise of quality and safety to the end user. For batteries that are destined for a larger pack, like those used in electric vehicles or laptops, there's an extra step sorting and grouping. No two batteries are ever perfectly identical. There are always tiny variations in capacity and internal resistance. To build a high-performance battery pack, it's essential that all the cells within it are matched as closely as possible. Automated systems sort the finished cells into hundreds of different grades based on their test results. This ensures that, when the cells are welded together into a module, they'll all charge and discharge in unison, maximizing the pack's performance and lifespan. Finally, the batteries that have passed every single test are ready for their journey out into the world. They're laser-etched with serial numbers and date codes for traceability. Depending on where they're headed, they might be wrapped in a protective PVC sleeve or placed into branded packaging. They're then carefully packed into special boxes, with dividers to keep them from touching and short-circuiting during transit. These boxes are labelled according to strict regulations for shipping lithium-ion batteries. So, from a collection of refined powders and foils, a safe, reliable and powerful source of energy has been created, tested, and is now ready to power our world. The most profound impact of modern batteries, honestly, can be felt right in the palm of your hand. The smartphone, a device that's become almost an extension of ourselves, just wouldn't exist without the energy density and slim profile of the lithium-ion battery. This small, rechargeable power source is what allows a supercomputer to live in our pockets, connecting us to a global network of information, communication, and entertainment. It's what powers the brilliant display, the powerful processor, the high-resolution camera, and the array of sensors that make our phones so capable. The freedom to navigate a new city, capture a precious memory, or talk to a loved one across the globe, that's a freedom granted by the battery. But this revolution goes way beyond just the smartphone. Think about the whole ecosystem of personal devices that now orbits our daily lives. Wireless earbuds, smartwatches, fitness trackers, portable speakers. All of these have become totally commonplace, seamlessly integrating technology into our routines. Each of these devices owes its existence to the development of tiny, efficient batteries that can hold a charge for hours or even days. The ability to listen to music on a run without tangled wires, or to track your health metrics around the clock, is a direct result of the relentless march of battery innovation. We've really become used to a world where our technology is not just powerful, but also personal, portable, and persistent. The impact of this personal power is deeply psychological. It's fundamentally changed our expectations of technology and our relationship with the world around us. We're no longer tied to a desk or a wall outlet to be productive, informed, or entertained. This has given rise to a culture of mobility and constant connectivity, for better or for worse. Honestly, the anxiety of a low battery warning is a modern phenomenon that shows just how dependent we've become on these pocket-sized power plants. The battery hasn't just powered our devices, it's rewired our social habits, our work culture, and even our very perception of time and space. This personal tech revolution, kick-started by the battery, just keeps accelerating. The next generation of wearable technology, augmented reality glasses, and interconnected smart devices will demand even more from their power sources. They'll need to be smaller, last longer, and charge faster. In many ways, the story of personal technology is really the story of the battery. As battery technology evolves, so too will the devices that shape our digital identity and mediate our experience of the modern world. The small batteries we carry with us every day aren't just accessories. They're the engines of our increasingly connected and mobile human experience. The liberating power of the battery has, really radiated outwards from our pockets, fundamentally transforming the spaces where we live and work. Inside the home, a quiet revolution has taken place, one cord at a time. Think of the humble vacuum cleaner. Once a bulky machine that had to be dragged from room to room, tethered by a frustratingly short cord, it has been reborn as a lightweight, powerful, cordless stick vacuum. This freedom of movement is made possible by compact, energy-dense lithium-ion battery packs. And honestly, this same principle has been applied to countless other household tools, from kitchen blenders and mixers to garden trimmers and leaf blowers, making daily chores easier and more efficient. The modern workplace has been similarly untethered. The rise of the laptop computer, powered by increasingly capable batteries, untied the professional from their desk. This trend has only accelerated, leading to the remote work culture that is now a reality for millions. The ability to work from a coffee shop, a park, or a home office is predicated on having a device that can last for hours without being plugged in. High-capacity batteries also power a new generation of cordless power tools on construction sites, giving workers unprecedented freedom and safety, eliminating the hazards of tangled extension cords and the need for noisy, polluting generators for every task. This cord-cutting trend is about more than just convenience. It represents a fundamental shift in our interaction with objects and spaces. It changes how we design our homes and offices, as the placement of power outlets becomes less of a limiting factor. It allows for more flexible and dynamic environments where tools and technology can be brought to the task, rather than the other way around. The battery acts as an invisible enabler, simplifying tasks, removing constraints, and creating more fluid and adaptable living and working spaces. It removes a layer of friction between us and the tools we use to shape our world, making our interactions more direct and intuitive. As we look forward, this trend is set to continue. The smart home, with its network of wireless sensors, cameras, and locks, relies on long-life batteries that can operate for months or even years without needing attention. The future of robotics, both in industrial settings and as domestic assistants, will depend heavily on advancements in battery technology that allow for longer operational times and faster charging. The battery is not just removing cords. It is removing the physical and logistical barriers that once defined the boundaries of what was possible within the four walls of our homes and workplaces, paving the way for a more connected and automated future. Perhaps the most visible and honestly transformative impact of battery technology is happening on our roads. The rise of the electric vehicle, or EV, represents one of the most significant shifts in personal transportation since the invention of the internal combustion engine itself. At the heart of every EV is a massive battery pack, typically weighing hundreds of kilograms and composed of thousands of individual lithium-ion cells. This pack is the car's fuel tank and its engine, all in one, It stores the electrical energy needed to power the electric motor, propelling the vehicle silently and with zero tailpipe emissions. This is a complete reimagining of what a car is and how it works. The impact of this shift is, well, monumental. On a personal level, EVs offer a completely different driving experience. They deliver instant torque, resulting in smooth, rapid acceleration that feels unlike any gasoline car. They are remarkably quiet, reducing noise pollution in our cities and creating a more serene cabin environment. The convenience of refueling at home, simply by plugging the car in overnight, changes the entire dynamic of vehicle ownership. The weekly trip to the gas station is replaced by the simple act of plugging into a wall, a routine as common as charging a smartphone. This convenience is a powerful driver of adoption. On a societal and environmental level, the transition to electric mobility powered by batteries holds immense promise. Widespread EV adoption can dramatically reduce urban air pollution, leading to cleaner air and better public health in our cities. When charged with electricity from renewable sources like solar and wind, electric vehicles offer a pathway to decarbonize the transportation sector, which is, one of the largest contributors to greenhouse gas emissions. The battery is therefore not just a component in a car, it is a critical tool in the global effort to combat climate change, representing a tangible and scalable solution to reduce our reliance on fossil fuels. However, this battery-powered transformation is not without its challenges. The demand for raw materials like lithium, cobalt, and nickel is soaring, raising questions about sustainable mining practices and supply chain ethics. Building out a robust and rapid public charging infrastructure is a massive undertaking that is crucial for long-distance travel. And the end-of-life management for these enormous battery packs presents a complex recycling and disposal puzzle that the industry is actively working to solve. The electric drive is reshaping our world, but it is also forcing us to confront new and complex questions about energy, resources, and the true cost of mobility. Beyond our personal devices and vehicles, batteries are beginning to play a new and critical role on a much larger scale, stabilizing our electrical grids. The world is increasingly turning to renewable energy sources like solar and wind power to meet its electricity needs. These sources are clean and sustainable, but they have a fundamental challenge: they are intermittent. The sun does not always shine, and the wind does not always blow. This variability can make it difficult for grid operators to perfectly match electricity supply with demand at every moment of the day, which is essential for a stable power system. This is where large-scale battery storage systems come in. These grid-scale batteries, often housed in large buildings or rows of shipping containers, are filled with thousands of battery modules, much like those in an electric car. They act as giant energy reservoirs. When renewable energy production is high but demand is low, for example on a sunny and windy afternoon, these batteries can absorb the excess electricity and store it. Then, when demand peaks in the evening and the sun has set, the batteries can discharge that stored energy back into the grid, ensuring a reliable and continuous supply of power. This capability is a game changer for the energy industry. It allows us to capture clean energy that would otherwise be wasted and deploy it when it is most needed. This makes the grid more resilient, efficient, and less reliant on peaker power plants, which are often the most polluting and expensive fossil fuel plants that fire up only to meet high demand. In essence, batteries help to smooth out the peaks and valleys of renewable energy generation, creating a more stable and reliable foundation for a clean energy future. They are the missing piece of the puzzle that makes a 100% renewable grid a tangible possibility rather than a distant dream. These systems are also being deployed at a smaller scale, in homes and businesses. A home battery system, often paired with rooftop solar panels, allows a homeowner to store their own solar energy for use at night or during a power outage. This provides energy independence and can lower electricity bills. For the grid, millions of these distributed home batteries could one day be networked together to form a virtual power plant, a vast, decentralized energy storage network that can help balance the grid. In this vision, batteries are not just passive consumers of power. They are active participants in creating a smarter, cleaner, and more resilient energy system for everyone. While we often focus on the batteries in our consumer gadgets and cars, some of their most important work happens quietly, behind the scenes, in systems where failure is not an option. In hospitals, batteries are the silent guardians that ensure life-saving equipment continues to run during a power outage. Ventilators, infusion pumps, surgical equipment, and patient monitors all rely on uninterruptible power supplies backed by batteries. These systems provide a seamless bridge of power in the critical seconds between a grid failure and the startup of backup generators, a period where even a momentary loss of power could have devastating consequences. This concept of backup power extends to the vast infrastructure that underpins our modern society. Data centers, the digital hearts of our global economy, are protected by massive rooms filled with batteries to ensure that our cloud services, financial transactions, and communication networks never go down. Cell phone towers have battery backups to maintain service during emergencies, which is often the only way for people to call for help or receive critical information. Even traffic lights have small battery systems to prevent gridlock and accidents during a blackout. In these applications, the battery is a crucial form of insurance, a silent sentry waiting to perform its vital function at a moment's notice. The impact is also deeply personal and life-sustaining. For millions of people around the world, a tiny, specialized battery is the only thing keeping them alive. Implantable medical devices like pacemakers and defibrillators use highly reliable, long-lasting batteries to regulate a person's heartbeat for a decade or more. The chemistry in these batteries is designed for ultimate reliability and safety within the human body, providing a steady, low-power current year after year. Similarly, hearing aids and cochlear implants rely on tiny, powerful button cells to restore a connection to the world of sound. For these users, the battery is not a convenience, it is a lifeline. This unseen impact highlights the profound trust we place in battery technology. We trust these devices to start our cars, to protect our data, and in many cases, to keep us healthy and safe. This trust is built upon the decades of research and the meticulous manufacturing and testing processes we have explored. From the global data network to the beating of a human heart, batteries provide the reliable, portable, and life-sustaining power that supports the hidden framework of our world. They are the quiet heroes of our technological age, working tirelessly in the background to ensure our world runs smoothly, safely, and without interruption. As we stand on the cusp of a new energy era, the limitations of current lithium-ion technology are becoming increasingly clear. While it has powered our modern world, the search for its successor is one of the most urgent quests in materials science today. Scientists and engineers around the globe are in a race to develop the next generation of batteries, striving for a breakthrough that will be safer, more powerful, and built from more sustainable materials. The goal is to create a battery that can charge in minutes instead of hours, last for thousands of cycles without degrading, and eliminate the reliance on expensive and ethically challenging materials like cobalt. This is the holy grail of energy storage research. One of the most promising contenders in this race is the solid-state battery. This technology replaces the flammable liquid electrolyte found in today's lithium-ion cells with a thin, stable layer of solid material, such as a ceramic or a polymer. This simple change has profound implications. By removing the flammable liquid, solid-state batteries promise to be far safer, virtually eliminating the risk of fires that can plague current designs. Moreover, a solid electrolyte enables the use of a pure lithium metal anode, which has a much higher energy density than the graphite anodes used today. This could lead to batteries that store twice as much energy in the same space, meaning an electric car could travel much farther on a single charge. Another exciting area of research focuses on chemistries that move beyond lithium entirely, using elements that are more abundant and cheaper to source. Sodium-ion batteries, for example, operate on a very similar principle to lithium-ion but use sodium, an element that is thousands of times more common and can be extracted from seawater. While currently less energy dense than their lithium counterparts, they are a promising low-cost solution for large-scale grid storage, where weight is less of a concern. Similarly, researchers are exploring zinc-ion, aluminum-ion, and even iron-air batteries, each offering a unique set of advantages in terms of cost, safety, and material availability for a sustainable energy future. The path from a laboratory breakthrough to a mass-produced product is long and fraught with challenges. New battery chemistries must not only perform well, but must also be manufacturable at a massive scale and at a competitive cost. It requires developing entirely new supply chains, retooling factories, and ensuring the technology is durable and reliable over many years of use. While it may be some time before these next-generation batteries are powering our phones and cars, the incredible pace of innovation is undeniable. The future of batteries promises not just an incremental improvement, but a fundamental leap forward in how we store and use energy across society. The explosive growth of batteries, particularly the massive packs used in electric vehicles, presents a monumental environmental challenge. What happens to them at the end of their life? A single EV battery can contain hundreds of kilograms of valuable and hazardous materials. Simply discarding these batteries in landfills is not only an environmental hazard, but also a tremendous waste of precious resources. The future of batteries must therefore be a circular one, where the end of one battery's life becomes the beginning of another's. This means creating a robust and efficient system for collecting, dismantling, and recycling every battery we produce. The goal of battery recycling is to create a closed-loop system. In this system, old batteries are treated as a rich urban mine from which valuable materials like lithium, cobalt, nickel, and copper can be extracted and returned to the manufacturing supply chain. This reduces our dependence on new mining, which can be environmentally destructive and geopolitically complex. By recovering these materials, we can lower the carbon footprint of battery production, conserve natural resources, and create more resilient and localized supply chains. Making recycling an integral part of the battery life cycle is essential for the long-term sustainability of our electrified world. Currently, two main methods are used for lithium-ion battery recycling. The first is pyrometallurgy, a brute force process that involves smelting old batteries at extremely high temperatures to recover a few key metals like cobalt and nickel. While effective, this process is very energy intensive and does not recover all materials, such as lithium. The more advanced method is hydrometallurgy, which uses a series of chemical leaching processes to dissolve the battery materials into a solution, from which high-purity metals can be selectively recovered. This method is more precise and can recover a wider range of materials, including lithium, with a lower energy footprint. Building a truly circular battery economy requires more than just efficient recycling technology. It demands collaboration across the entire industry. It means designing batteries from the outset with disassembly and recycling in mind, a concept known as design for recycling. It requires new regulations and incentives to encourage consumers and businesses to return old batteries. It also means developing a sophisticated logistics network to safely transport and handle millions of used battery packs. As we build more batteries than ever before, we have a unique opportunity and a critical responsibility to build a sustainable, circular system that will power generations to come. The future of batteries is not just about new chemistries and materials. It is also about the intelligence that manages them. A modern battery pack, whether in an electric car or a grid storage system, is far more than a simple collection of cells. It is a sophisticated cyber-physical system, governed by a complex piece of software known as a battery management system, or BMS. This embedded software is the brain of the battery, constantly monitoring the state of every cell, balancing their charge, managing temperature, and ensuring the pack operates safely and efficiently within its limits. As batteries become more powerful, the role of this software becomes ever more critical. The next great leap in battery performance will come from making this software smarter, primarily through the use of artificial intelligence and machine learning. AI algorithms can analyze vast amounts of real-world data from millions of batteries operating in the field. By learning from this data, an AI-powered BMS can create a digital twin, a virtual model of the battery that understands its unique health and aging characteristics. This allows the system to make much more accurate predictions about the battery's remaining range, its state of health, and its overall lifespan, providing users with more reliable and transparent information about their device's power source. This intelligence can also actively extend the life of the battery. For example, an AI system could learn a user's daily charging habits and optimize the charging process to minimize stress on the battery cells. It might delay charging to 100% until just before the user typically unplugs, as keeping a battery at full charge for long periods can accelerate degradation. In an electric vehicle, the AI could precondition the battery temperature before a fast charging session to maximize charging speed and minimize cell damage. These small, intelligent optimizations, performed consistently over the life of the battery, can add up to a significant increase in longevity and performance. Ultimately, software and AI are becoming a crucial layer of safety. By constantly analyzing subtle changes in voltage, temperature, and internal resistance, AI can detect the early warning signs of a potential cell failure long before it becomes a dangerous problem. It could then alert the user or even automatically isolate the faulty part of the pack to prevent a thermal runaway event. This fusion of advanced chemistry with intelligent software is transforming the battery from a passive component into an active, self-aware system. The future battery will not just store energy, it will manage it with an unprecedented level of intelligence, making our devices safer, longer lasting, and more reliable than ever before. As our journey from the first spark of discovery to the automated factory floor comes to a close, we are left with a vision of a future profoundly shaped by the humble battery. The continued evolution of this technology is not merely about creating better gadgets or faster cars. It is about fundamentally reshaping our relationship with energy itself. We are moving from a world built on centralized, combustible power to one that is decentralized, renewable, and stored. The battery is the key enabling technology for this historic transition, the linchpin that connects a clean energy source like a solar panel to a final use like a home appliance or an electric vehicle. Imagine a world where energy is abundant, clean, and accessible to all, where remote villages, far from any centralized grid, can be powered by local solar panels and community battery storage, unlocking new opportunities for education, healthcare, and economic development. Imagine cities where the air is clean, free from the noise and fumes of combustion engines, and the entire transportation fleet, from cars and buses to delivery drones and even short-haul aircraft, runs on silent, efficient electric power. This is not a distant fantasy. It is the tangible future that battery technology is helping us build, one cell at a time. The battery also promises to make our energy systems more resilient and democratic. When millions of homes, businesses, and vehicles are equipped with their own battery storage, they form a vast, distributed network of energy resources. This network can support the grid during times of peak demand or emergencies, reducing the likelihood of large-scale blackouts. It gives individuals and communities more control over their energy, turning them from passive consumers into active participants in a cleaner, more robust energy ecosystem. The battery empowers us not just with portable power, but with energy, independence, and security in an uncertain world. The story of the battery is ultimately a story of human ingenuity and our relentless pursuit of a better future. From a simple pile of metal discs to the incredibly complex and intelligent power packs of tomorrow, the battery is a testament to our ability to unlock the hidden potential of the world around us. It is the silent, unseen engine that will power a cleaner, smarter, and more equitable world. As we continue to innovate, refine, and perfect this essential technology, we're not just charging our devices, we are recharging our planet and empowering the generations that will follow. The future is electric, and it will be carried in the heart of a battery.